So, good evening, everyone. Today is our lecture 5 of NPTEL Algebra 1 course, and so the syllabus or the contents of this week was tree groups and generators and relations of symmetric group. So we have been doing for the last two class tutorials about silo groups and things, but I thought maybe we should start with three groups today, and with time permitting we'll be doing symmetric groups and maybe some related programs to silo groups and symmetric groups. So let's start with symmetric groups. uh, so yeah so let's start with three groups. So the question one is that prove that three groups are torsion free. So we know what is a free group, right? It is a group generated by a finite number of or infinite number of elements, such that order of every element is infinite and unique. Like that, their product should be uh, unique, So, and also there are some forms called normal forms, such that if you cannot write it as in the element x dot x inverse should not be there. They should be treated as identity and should be ignored, like the minimal form of the conjugate. Like a free group is the uh, is the quotient is a equivalence collection of equivalent classes, right? Where the equivalence relation is defined by we say by a relation such that you go from one word to another by a finite time operation that is introducing x dot x inverse in between the elements. So you can find it in the lecture notes. I will not go into the detail, but anyway, so okay, let's start with our solution. Let A be a free group on a set X. So X is the set of generators. Yeah, we may, as I said, we may consider the elements of F as in the normal form. That is, every element every element W in F can be written uniquely in the form W is to x1 t1 xk to the power tk xk to the power tk, where xi belongs to capital X and li belongs to z for all I equals to 1 to k. So write it as t here. And there should be another thing to notice: xi not equals to xj for I not equals to j. So what I was telling earlier, observe that xi and xi inverse have infinite orders. Because this is a free group, so uh, all the powers of this, like this should be linear independent over z, so that is why they have infinite orders, at least of the generators. Now,
Good evening, sir.
yeah.
Sir, actually, I have joined late. Can you please explain the idea how we are heading proving this question?
Oh, so uh, yeah, pretty much this is a like basic question related to why free groups are torsion free. So uh, you I hope you already know the basic definitions and free groups and things. So
Yes, sir.
this is a group which is primarily a set of equivalence classes where a relation is defined by a finite number of operations of uh, adding xi inverse, these kind of things. So we are trying to show that a free group related to a set is torsion free. That means every element of this group has infinite order. That means that if x to the power k equals to identity of the group, then k should be then x should be identity itself. So that is our primary goal. Now,
Okay, sir.
yeah. So this way we have started our solution. Now, okay. So coming back to the proof, let w equals to x1 t1 and xk to the power k bn arbitrary uh, non-identity element of f. Now w square should be x1 to the power t1 to xk to the power tk, and again x1 to the power t1 to the power xk to the power tk. Note that if x1 to the power l1, sorry, t1 not equals to xk to the power minus tk, that means if x1 to the power t1 is not an inverse of xk to the power tk, then for any n, wn is non-identity, right? Because uh, for the first step of concatenation you are stuck, so the question of identity does not come here, and we are done. since n was arbitrary, so you see that any element has infinite order. But if x1 to the power t1 equals to xk to the
Sir,
power, yeah,
excuse me, sir.
yeah,
So you have taken a W square in the
w
last
square,
third
yeah,
line.
yeah, yeah, yeah.
Okay, okay.
Yeah. Now if x1 to the power t1 equals to xk to the power minus tk, then in w square these two elements cancel and gives identity. So what I'm trying to say is that look at this product. Now if these two gets cancelled out, we go to our second members. If they gets cancelled out, we go to our third members. So this is the iterative process we are following now. And but it may happen that x2 to the power t2 equals to xk minus 1 to the power minus lk tk minus 1. Oh, sorry, tk minus 1. Then in w square these two elements cancel and gives identity. And not just yet, and uh, and gives w as the form x1 to the power t1, x2 to the power t2, dot 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 x to the power x2 to the power minus t2, and x1 to the power minus t1. Then continuing like this, we reach to an element x1 to the power t1, x2 to the power t2, dot dot xi to the power ti, xi to the power minus ti, x2 to the power minus t2, and x1 to the power minus t1. But this implies what? But this implies that w is identity, right? So there exists I such that when we take powers of w, then the powers of xi increase. Since xi has infinite order, we obtain W is infinite order. So the, that is how we complete this proof. So since there are not many people, uh, Akanksha, you tell me that you are comfortable with this exercise on free group, or we should do some problems related to symmetric group, or because I'm fine with anything.
Actually, sir, I have less knowledge about free groups and I know more about symmetric groups.
So I think free group
Oh,
is may help you, or
yes, sir. Actually, yes, sir.
yeah, I mean yeah, that way it should be fine. Okay, so yeah, next okay, let's do this. Uh, Question 2. Let A be a free group and suppose that H is a subgroup with finite index. That means the cardinality of A mod H is finite. Prove that every non-trivial subgroup of F intersects H non-trivially. So can you try for 1 to 2 minutes, then let me know if you find anything, or else of course I will do the solution.
Okay, sir. Sir, I can't find anything. You do the solution.
Yeah, it's okay. Uh, so this actually uses symmetric group also little bit. Okay, let's try to solve this. So the group H has finite index in F. This implies that F acts uh, on the right. I mean, this means that this is a right action to the set omega h x1 to h xn of the right cosets of h in F, right? I mean, this means that F acts on uh, F by H. I mean this. So that means what? That I told in earlier TS sessions that this means that there is an equivalence morphism. That means there exists a homomorphism phi from F to symmetric group generated by omega, and the kernel of phi is what? I mean, the kernel should be what? The elements of F uh,
which goes to the identity of
identity.
symmetric
Yeah.
group.
So this means what? That this is nothing but the intersection of h xi, right? Because if you multiply them, then they go to the every same element. If you cannot solve with this, then this is an exercise, you can check, but this is trivial. Hence,
So what is the map here?
okay, so this like the action map. So if x is here, then x will go to h, like, okay, let me write it properly. Phi x to omega. So this would h xi go to xi x or x inverse. Think this should be better by if you write it as uh, x inverse, because for I, because to do this na, that x1 x2 of write it this way, x prime x double prime of h xi should be x prime of a x double prime of h xi. So if you check this, then you will see that h xi, I mean the map should be h xi goes to h xi x inverse, or another way you can write it as h x xi, whatever suits better.
Sir, can you explain it again? This map you
Okay,
have written on the right.
so okay, let's start with uh, this thing that h xi goes to h xi x inverse, right? uh, x prime, and we have to satisfy this, right? xi. Because identity case is trivial, all we have to do check is this associativity. So say it is hxi double prime inverse and x prime inverse, right? It is coming from the first equation, right? Like this is better if you check this, because I have defined it as like this. So if you act with x dot this will go to h xi x inverse. So this way you are getting this, and following this you'll be seeing that x prime going to h xi x prime inverse, and again this will be h xi so double prime inverse x prime inverse. Now is it clear? Oh sorry, what did I do? Yeah.
Yes, sir.
So my like the pattern of writing is little bit confusing, but if you actually hear me and follow these uh, things, then I think it will be clear. So why I took the inverse on the right side, is it clear? To satisfy this uh, this transitive property, right? Not transitive, say associativity. Okay.
Yes, sir.
Please again let me know if you have doubt, because that is the goal, to let you make understand. Okay. So hence f by car phi is a finite group. Coming back to the map, if you see, so our map is this, and obviously the uh, order of the symmetric group is n factorial, right? So the image is a subgroup of this, so that is finite. So the and that is isomorphic to f by car phi, so which is a finite group. Now let sorry let k be a non-trivial subgroup of f, and let we take a non-identity element from k, right? Then you see that then this w to the power n factorial is not identity, right? Because what we just proved in the first case, that proved that free groups are torsion free, so that every element has infinite order, right? Then w to the power n factorial is also a non-trivial element, uh, right? But
Oh, yes, sir.
you see that w n factorial belongs to car phi, right? Which is a subgroup of H, because HXI they are this this intersection, if you check properly, then this is a subgroup of H. Hence this non-trivial element Wn factorial belongs to K intersection, because Wn factorial uh, we took W from K, so its power should be in K, and uh,
Sir, why W power n factorial belongs to kernel?
I think I made a typo. Let Sorry, what you said?
Sir, I asked why W to the power n factorial
Hmm.
belongs to kernel phi. If it belongs to kernel phi, then it should uh, then phi of this must be equal to identity of phi. No. Uh, what I am asking is
Hmm.
why it belongs to kernel phi.
Yeah, yeah. Let me see. I am trying to find what I did wrong here. Find proof. That give a non-trivial subgroup proof. Yeah, I am also like getting confused. When I wrote this down. So W n factorial belongs to kernel phi means that this map should be identity, right? This phi W n factorial. Okay. So order of f kernel phi is n factorial, right? Yeah. So order of f kernel phi, f by kernel phi is n factorial, right? Because this,
Excuse me, sir.
yeah,
Sir, I lost my
yeah,
connection. So
yeah,
can
yeah,
you please
yeah.
explain that again?
The symmetric group has order n factorial, right?
Yes, sir.
So now uh, subgroup f by kernel phi, this has, okay, okay, let me tell you properly. So this
So in the last, you were explaining why W to the power n factorial belongs to
yeah, yeah,
kernel of
yeah,
phi.
I am explaining that only, but First, I am
Okay, okay.
stating a fact that from this map, yeah, you notice that it has order n factorial, right? The symmetric group, because it has n elements, so we
Yeah,
know,
yes, sir.
yeah, it has,
I know that.
yeah. Now
Okay.
f by kernel phi is a subgroup of this, right?
Oh, yes, sir.
By the
By
isomorphism,
fundamental
yeah,
theorem of
yeah. So the order of
homomorphisms.
f by kernel phi should divide n factorial,
Yeah,
right?
yeah.
Say it is k, right? Then since you took w from k, now it is a random element from f, right? So then w bar belongs to f by car phi. I mean this is an element of this. So w to the power k should belongs to car phi, right?
So K is F by kernel phi, F mod kernel phi.
No, no, no. I okay. This let this order is L, right? F by kernel phi. Its order
Oh,
is L.
okay.
Let
Okay.
then w to the power L, w bar to the power L belongs to car phi, right? Uh, any element from a finite group, if you uh, uh, like uh, order of,
Okay, so
yeah, you are getting it. Order of any element should divide the order of the whole group. So
it's
L to the power order of the group,
and sir, a zero, or you can say identity of this F mod kernel phi is basically kernel phi.
yeah,
So when you put the power L, it will
yeah,
go to that kernel phi.
yeah, right?
Yeah.
I mean
Okay,
I
sir.
mean
Now,
if I write more properly, this should be E bar, that implies that W to the power L belongs to kernel phi, right? E bar is the identity element of this group. Is it clear, or shall I say again?
yes, sir. No, no, it's clear, sir.
Okay, so again L divided n factorial. So n factorial is something like L R, right? So that implies that WL to the power R belongs to kernel phi. That implies that W to the power n factorial belongs to kernel phi, right?
Okay, sir.
Clear, right?
Yes.
Yeah. I actually forgot uh, why I wrote those. And yeah, already I told that kernel phi is a subset of H. So this is a subset of K intersection H. So this proves our original claim, that prove that every
Sir,
non-trivial, yeah,
it
yeah,
was a subset of H because we have defined kernel phi as the intersection of cosets of
not
H.
defined, it can be proved.
Okay, okay.
Yeah. So yeah, now so actually we have completed the proof. If you see that every non-trivial subgroup of F intersects H non-trivially, so we took a random non-trivial subgroup K, and showed that there exists a non-trivial element in the intersection, right?
Yes, sir.
Okay, let's do another problem regarding. So yeah, ask this kind of questions, and I wonder why other people have stopped uh, attending. Last semester also, I almost did 10 to 11 class only recording. First two class, that was like 7 to 8 people. Then suddenly, I think
I
people.
don't know, sir.
I think people get busy or something, or they just simply prefer the recording.
Actually, sir. So that they can watch into 2x.
Yeah, I mean, into 2x so that 1 or 2 hour lecture can be shrink down to 1 hour. Okay, so this problem is that if I have a free group of rank greater than 1, that means it has at least two generators, then it has trivial center. Trivial center means that only element which commutes with everyone is the identity. So you try this for uh, 2 or 3 minutes. It should be easier, and I will be coming back.
Sir, what is rank
Oh,
of
rank
rank?
means the number of independent generators that
Okay, okay, okay.
say Z cross Z. This is a free group, right? And it has two generators. It has many generators, but yeah,
0, 1.
yeah,
Yeah.
yeah. That means the three diamond. You can think of it as vector space over Z, but it's not
Okay, okay,
logically
sir.
true, but gives you a feel. Yeah. Okay.
Sir, we can do it by contradiction. If we assume it has no trivial center,
Huh.
and then if we show that the other elements other than identity,
Huh.
which we take,
Huh.
they end up to a identity only.
Hmm. Okay, okay, okay. I'm getting. Oh, okay. If I write this down formally, uh, solution. Let small w be x1 to the power l1 to xn to the power ln, uh, be an element of a center of a free group of rank greater than 1. Now if x1 not equals to xn, then see that x1 to the power l1, xn to the power ln at x1 not equals to x1, x1 to the power l1, xn power ln, right? Because for free groups, unless it is a free abelian group, the orders are like they hold their stance. Like the if you change the orders, the elements will be changed. Uh, like in jet like in dihedral group, or like every non-trivial free group, there are examples that if you change the order, the elements will be changed, and this equals to x1 to the power ln plus 1 dot xn to the power ln. So yeah, then if x1 not equals to xn, then you see that it cannot commute with x1, so this does not belongs to center of the group, right? So we have to uh, so small w does not belongs to center of C group F, does not belongs to, because it does not commute with x1, right? Commute with x1. Now if x1 equals to xn, then consider w x2 x1. So again, by uniqueness of writing, w x2 x1 not equals to x2 x1 w. So see, my xn was arbitrary, right? So I can repeat this step up to n times and show that this does not happen. So only thing is possible for w to be in the center is that, so only, okay, let me write it more precisely. So we can repeat this case iteratively or inductively and show that and show that w does not belongs to z of f if n greater than 1. Now if uh, uh, so this means what, that this means that this means only element of zf is the identity. But so this completes our question. But if you see that only generator of f is x, if x is only generator of, x is the generator of f, then every element is of the form xn. So this implies that xm dot xn should be xm plus n, and this would imply that xm dot xn. So then they would commute, right? So the group would be abelian, free abelian group. So this completes our proof, but this is remark. Okay, so we will do another one or two problem regarding free group, then we can move on to uh, okay. So th- this is this is a similar question to what I just said, and after that we will be doing some symmetric group problem. So yeah, did you sit for the CSR net this time last time?
Oh, yes, sir.
So how was its result got out, right?
So it's not that good. I got 75
Okay.
marks.
What was the cutoff? No, I think cutoff has not been.
Yes, the cutoff is not announced yet.
But anyway, it will be so. Most of us just do not get time during MSc to prepare.
Yes, sir. Actually, I'm preparing it right now
Yeah, yeah, yeah.
for the December one.
Yeah, I mean, if it motivates you, it also took me like 2 year to get PhD after MSc. So it's fine. Most of us takes time. And,
Okay, sir.
okay, so see that this question has that what I just said, that if it has a single generator, then it will be abelian, but and uh, abelian, but this says that, see, if it has single generator, then it is infinite cyclic, right? Because uh, a free group is torsion free, so with single generator it has no torsion element, so it should be infinite cyclic, and cyclic group implies it is abelian. But the converse
Yes,
is
sir.
also true, that if a free group is abelian, then it is infinite cyclic. Okay. Okay, so let us do this. It is clear that uh, an infinite cyclic group is abelian, and it is also free. Okay, let me write why it is free. Because for any group G and a function sigma from x to G, say uh, sigma of x equals to small g, then you see that uh, this commutes, right? Small x, if f is your free group generated by small x, then you will see that this commutes, right? This is your, say, sigma to free group, and this is your gamma from x to g, gamma restricted to small x, and say this is my beta, and this gives that beta is an isomorphism, So G is free. This is just routine check and comes from the definition. You can check it, and and the converse follows from the previous problem. How? I mean, you just see that it is okay. So free group is abelian. So that means that its center is the whole group, right? But we have seen that with n greater
Yes, sir.
than 1, its center is trivial. So it should have only one generator, and that means it is infinite cyclic, because at the first we proved that it is also torsion free. So that way uh, it is we are done. Okay, so maybe let us do some NBHM problem for symmetry groups. Is it okay?
Yes, sir. Sir, in this last question,
Yeah,
uh, where you have defined this triangle,
yeah, yeah, yeah.
these functions, can you repeat them,
Oh,
please?
so um, there is there is a thing that the universal property for the free groups that so okay, say let us define what is a free group. I mean, if it has not been done in the classes properly, uh, you can okay, given a non-empty set X and a map theta from S to F in where into a group.
Sir, you are defining what is free group.
Yeah, free group. So that way it will be more clear why G is your free group. I mean, I had G, which is infinite cyclic. Then uh, then I took the free group generated by X, right? And
Yes,
normally
sir.
there is a map from the set of generators to the free group generated by them, and you already
Yes,
had a map that gamma from capital X to G. I just restricted it to singleton X, and I am showing that there is a isomorphism between F and G. This is my
okay.
goal. And if I define free group by how I wrote it, then it will be clear why this is a free group or why this is an isomorphism also. So given a non-empty
Yes,
set capital X and a map theta from sorry X to F, uh, the pair the pair F comma theta is said to be a free group on X if for any function alpha from X to G to any group G, there is a unique morphism alpha tilde from F to G such that alpha equals to alpha tilde transpose theta. That means if you make the triangle, it should be first theta, that is your capital X to F, then it should be alpha from capital X to G and followed by alpha tilde. So it is saying that theta is already given, and your alpha is also given, and for every alpha you will get a alpha tilde, And modifying this, uh, if you can show that alpha tilde is an isomorphism, then you see that G is isomorphic to F and F is already a free group, so that is why G is a free group. Now is it clear? I think this,
Yes, sir.
yeah. Just try to think about it. Maybe I will provide a note what I am following in the group. Just I mean there,
Yes, sir.
yeah,
If
yeah,
you can do that.
yeah. You can just ping me after the class in the group. Then I will post it there, huh?
Okay, okay, sir.
Yeah. Okay. Okay. So yeah, shall I do more problems on free group or move on to symmetric group?
So you can move to symmetric groups.
Sorry.
You can move to symmetric groups problems.
Okay. Then I think I will be doing some NBHM problems because theoretical problems on symmetric groups are hazardous. Like I may make mistakes and also they will take time. But okay, okay, I will do some numerical problems only. Question 5, and this is symmetric groups.
I appeared for the NBT exam once
Okay, and how was it?
this year. So actually, I was not prepared. I just
That is fine. I mean, it takes.
actually, sir,
Huh?
uh, it, it sir,
Let think your
it was
voice.
sir, this exam. Yes, actually, sir, this exam is taken in our department only.
Okay.
So I just appeared.
Yeah, yeah, yeah. Do that. I mean, time management is also important, and unless you give such exams frequently, you cannot manage your time. Because it took me almost 1 year to. Also, 2010, in 2021 there was no net. But anyway, but it almost took me 1 year to just manage my time. So. Um, more exams you give, more you get a sense of how to prepare, and also how much time you should give to a single problem. In December also there will be an net, or in February there will be gate, I think. So yeah.
Yes, sir. In December, it will be NET, and in January, NBHM, and in Feb, GATE exam.
Yeah, yeah. Try to study try to study within a group. I mean, you send someone problem, I mean in a group, they solve it, and they send some problem, you solve it. I mean, this way, in less time you will get exposed to, like, you'll be getting exposed to more problems.
So I'm actually taking coaching from an academy for the NET exam.
Yeah, 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 the any academy is fine. I mean, because the basics are taught everywhere. So okay, so let's
Yes, sir. S7 contains element of order 10.
let us with a group of permutation. So what should be the? Can you give an example?
So,
So,
so we will take a cycle of 5 order and a cycle of 2 order.
uh-huh. So that way it can be, yeah. So that way, The answer is yes, and take 1, 2, 3, 4, 5. Say 6, 7. Right?
Yes. Yes, sir.
So can you believe that they gave this question in 2002, 6?
It was a basic question, actually,
But
sir.
nowadays they don't give, like, they actually give other questions. So okay, yeah, let's go to next one, question 6. So consider the permutation given by 1, 5, 2, 5, 3, 8, 4, 10, 5, 6, 6, 1, 7, 2, 8, 4, 9, 9, 10, 3.
Sir, the second entry,
2,
1
5,
goes to 5 and 2 goes to
5.
again.
1 goes to 5, 2 goes to, yeah, it should not, okay, okay, let me see. 1, 2, 3, 4, 5, 6.
Shit.
It should be 7. One of them should be
Yes, sir.
7. 7.
Either 1 goes to 7 or 2 goes to 7.
Yeah, let's say 2 goes to 7. So find the order. Should write it. 6, 5. Find the order of 5.
So it's 12.
Yeah, it is 12. So can you tell me the cycles you got?
So first is 156.
Huh?
Then a two order cycle 2 comma 7.
Huh?
And the third cycle is 3 8 4 10. 3 8 4 10.
So
And
you,
9 goes to 9.
yeah,
And then I take LCM of their lengths.
lengths, and you get it. Yeah. Okay, let's try this question. 7. What is the maximal order of an element in S7?
So 12.
Yeah, 3, 4 cycle are there. So,
Yes, sir.
but
It will be 12.
yeah. Okay, let's try this. Let sigma S7 be the permutation given by 1 2 2 1 3 5 4 4 5 7 6 6 7 3, which of the conjugated signal? Option A is 1 1 2 3 3 5 4 6 5 2 6 7 7 4, and B is 1 1 2 4 3 5 4 6 5 3 6 2 7 7.
So there are only two options, A and B.
Yeah,
So B,
because
because for conjugation we will see their cycle lengths.
yeah,
In the
because
question we have two length and three length cycles,
huh,
and in the option B we also have a three length cycle and two length cycle. But in option A we have three length two three length cycles. That's why they are not conjugate
yeah.
for option A.
So cycles of same lengths are conjugate.
Conjugate.
So the answer is B.
Actually, these questions are very trivial.
I am
Or
trying.
maybe, I'm preparing for net. That's why these are trivial to me.
No, no, it's fine. I'm also trying to find some uh, non-trivial questions.
Actually, sir, this time, at this these days, net have upgraded their level.
Yeah,
There are more many difficult questions.
they have reduced the number of seats, so that is why they're trying to uh, trying to fix the cutoff, but uh, hardening the question. So that is why. Okay, okay. Let us do this. It will involve some silo theorem, silo p-silo subgroup.
Okay, okay.
Select question one. Consider the symmetric group S20 and its subgroups A20 consisting of all even permutations. Let H be a silo 7 subgroup of A20. Pick the correct statements from below. Order of H should be 49. H must be cyclic. H is a normal subgroup of A20, and D any silo 7 subgroup of S20 is a subset of A20. The whole question is visible. Yeah.
So A is correct.
A is correct, yeah.
So for B, we need an element in A20 of order 49.
Yeah,
But I don't think so that there is an element of order 49. I'm
because
confused about that. 49 will not divide order of the group A20.
huh?
So there will be no element of order 49 if it was.
Yeah. So okay.
So
So
B is wrong.
solution. Yeah. Okay. Let me do this formally, huh? Order of
Okay.
A20 equals to factorial 20 by 2, which is hard to write, but anyway.
So no need to calculate.
Yeah. So order of silo 7 subgroup
7.
in A20 is 49, right? Because there is
This is
14,
highest power of 7 is
and
2
7.
here.
So 7 square is,
49.
yeah. So, so option A is true. But any group of 49, that is, uh, option B is not true, because any group of order p square is either cyclic or abelian, right?
Abelian.
Like, is either zp square or zp plus zp, right? But A20 is simple, right?
Yes, sir.
Because an is simple for n greater than equals to 5.
So then C is also wrong.
Yeah,
H can't be wrong.
yeah.
It's normal subgroup.
Because the they are only of this format, so they are normal. But n is simple, so normal subgroup of AN are E and AN.
Yes, sir.
So C is also wrong, but
So,
sorry.
so for B, the reason was that there is no element of order 49 in 820. In the B option, you
There
have
is no
to,
element of order 49, or is there?
so it can't be cyclic. It is only abelian.
Yeah,
And option D
and option D
may
was
be
that
correct.
because there is a theorem now that any odd order subgroup of Sn is contained in An.
Yes, sir, yes, sir. So there is a theorem, right?
Yeah, claim any odd order subgroup of Sn is contained in.
So can you prove this theorem?
Right now I have not prepared for this,
Okay, okay,
but okay, mention this. Maybe I will solve this and send it to the group.
okay, okay.
Uh, so this is true. But this is available in any standard textbook, I think, or in the exercise. Maybe most possibly it will be in the exercise. Okay. So okay, let us do another one. This was question 9. So question 10.
Sir, I have a question. Can you solve that? It's on the P silo subgroup
Yeah,
only.
yeah, yeah. You can send to WhatsApp, or where I
So
can check.
in that question, we have to calculate number of three silo subgroups in the ideal group of order 84.
Okay, send it to me.
Okay, sir.
Calculate number of three silo subgroups. Oh, in dihedral group of order 84. So this means that 84 means you are calculating as 2n equals to 84, right?
Yes, sir.
So,
So it was in the assignment,
oh,
and I
I
couldn't
cannot
find the
solve
answer.
assignment problems here.
So what?
Okay, okay, the date is gone, like, or the date is still active.
No, sir. It was in the last week.
Okay, then I can try calculate number of three silo subgroups in dihedral group of order 84. Okay, let me think. Uh, so solution. So first, let to break down
Prime.
84.
Yeah, it's a
So
prime factorization. It will be 2 to the power 2 into 3 into 7.
3 into 7.
Yes,
Oh,
sir.
uh, so last time we did similar kind of thing, na?
Yes, sir. We have done
Okay,
these type of questions.
so number of three shadow subgroups, it should be,
1 plus 3k divides 28.
yeah, 2, 2 square into 7 is 28. So for k equals to 0, it is 1 plus 28. For k equals to 1,
4
4
divides
divides
28.
28. And other than that, it is not possible, right?
So k is equal to 2. It
Oh,
will
yeah,
work.
k equals to 2, it works. So it will be
7 divides 28.
so there are three possibilities.
Yes, sir. And I'm unable to get the solution out of these three. But how to neglect the other two?
Okay, let's see.
And so the answer is 1.
It is unique.
Principal. But I don't know how.
Okay, let me think. So okay, so think of this way. So it is a dihedral group, say D of 42, and it has a rotation subgroup R, say C of 42. It is a rotation subgroup of index 2, right? So any element outside, uh, say any element outside C42 has,
So you have taken an example of 42.
sorry,
You have taken an example.
not.
Uh,
So dihedral
denoted.
group consists of two generators, right? One is rotation and another one is
Then I'm
reflection, right?
asking that 42.
So I just took the generator from the rotation group. Okay, any element, you are saying that it is an example or not, right? Are
Yes,
you,
the D42 is an example.
no. C42 is the rotation subgroup.
So you have taken the half of 84 or it's just
Yeah, Okay, okay, let me just say this. I'm just I'm just not taken the half of 84. C42 is the unique subgroup, that is the rotation. Okay, let me give this by in say D4. I have taken that dihedral group of a like a rectangle or square. So if this is A B C D, then one thing you can do is that rotate by this.
Yes, sir. Okay, now I got it.
Yeah,
Actually, you have taken that rotation.
yeah.
Okay, okay, okay.
So I took the this rotation subgroup, and there is
Yes, sir.
also reflection. So when you compose
Yes, sir.
rotation with reflection, you get the dihedral group.
Yes, sir. Yes, actually.
And since this subgroup has index 2, so any
So it
element,
is cyclic group, na? It is
this is
cyclic group
cyclic group.
also.
Yeah, yeah. So uh, for rectangle, you just divide 360 by 4, and
Yes, sir.
you rotate by 90 degree, you get your one. I mean, this is the generator rotating by 90 degree. So for 42, you should the generator should be 360 by 42, the angle.
Okay, sir.
Yeah. So any element outside this C42 has order 2, right? Because by D42, by C42, this is a cyclic group of order 2. So if you take any non-trivial element from here, it will have order 2, right? Because again, x bar square should belongs to C42, and that uh, I mean, this is identity, so this implies that this belongs to C42. This is identity, so this implies that x square belongs to C42. Is this clear? Hello?
Sir, explain that last
Yeah,
line.
okay, okay. There is also another method that any element outside C42 has order 2. That means that let x belongs to uh, D42 minus C42, right? That means this implies x bar not equals to E bar in D42 by C42, right? But uh, D42 by C42 has cardinality 2. So x bar square uh, equals to E bar in D42 by C42. This implies that x square belongs to C42. Is this clear now?
Yes, sir. Yes, sir.
So every 3 subgroup lies inside the cyclic rotation subgroup. That means in C42. That is in C42. Is this clear?
Yes, sir.
That means it is enough to check for 42 instead of 84. But now what you see is that C42 is cyclic, right? So there is a theorem na, every subgroup of order,
Of cyclic group is cyclic.
that is true, and also
And
it
it
is
will be unique.
unique. So it is clear, right? So it should be a unique subgroup, and unique Silo subgroup is normal. So we don't have to go to checking with Silo theorems. You just use this trick and Is it clear or still it looks fishy?
No, sir, I get it.
Yeah. Okay. Now we'll do another problem, then we'll finish it. Okay? Because I have to maintain at least 145 or
Okay, sir.
150. So question 11, and that will be let G denote the group S4 cross S3, then silo 2 subgroup of G is normal a silo 3 subgroup of G is normal. G has a non-trivial normal subgroup, and the option D is G has a normal subgroup of order 72. You can just try it and let me know.
Yes, but I fix your car, open door for you, buy flowers. I hospitalize men that tried to rob your purse last week. Is this not enough? Well, words matter too. Words did not kill my grandfather in the Great War. You want words? Okay, here. I make you poem. Roses are red. Vodka is clear. You drive me crazy like Lada switching gears. You like soft words? I fix your flat tire. Why you want romance when I save you from fire? I don't say I love you. That is Western fluff. But I build you a shed. Is that not enough? Sonnet.
Okay, so let us do this, huh? Uh, did you get any of the options?
No, sir. Actually, I'm not good with the product of groups.
Okay, okay. So okay, so the group was given is that S4 cross S3. Now order of the group, we got 4 into 6 plus 124. This means this should be, yeah. So the order of the two silo group, two silo subgroup 16,
So we
and
will treat it like a single group, like to clear its order and then find two silo and three silo subgroups,
yeah,
like we did in.
like
Okay,
you are asking like the previous problem or in general method, right?
sir. So in the present question, I'm asking ki like we have S4 cross S3
Uh-huh.
and we just normally calculated its order and we are finding two silo and three silo subgroups.
Yeah, yeah,
So we will find it like we have done in other questions.
yeah. Like in generally generally we do that number of two silo subgroups equals to 1 plus 2k dividing n, so 0 1 2 equals to, it should be 1 3 1 9.
So
So
for k is equal to 2,
k is equal to
it
2 is not
becomes
possible, right? Because for k is equal to 2 it would be, but k is equal to 4, it is possible. But actually this is little difficult at this point for me too, because the solution says that the number of two silo subgroups in S4 cross S3 are of the form D4 cross Z2. So apparently this is a standard theorem. So this implies that, not implies, uh, number of two silo subgroups is 9. Okay, I'm just writing the solution. You try to think, and if not then maybe you can discuss it in the next class, or just but two silo it should be 9. Why it cannot be 1 or 3? So D4 is of the form Z2 cross Z2, right? Because it has a two rotation group and two cyclic group, and they are
but sir D4 is non-abelian and Z2 cross Z2 is abelian.
no, no, no. Oh, by D4 I thought it is D2. That means it has order 8. Sorry. So how many subgroups of order 2 in are there in S3? Uh,
There are three.
there are three. And how many subgroups of like like D4 in S4? So that is the trick, I think. So subgroups, isomorphic number of subgroups, but number of subgroups isomorphic to D4 in S4 are should be 3, and number of subgroups isomorphic to Z2 in S3 is 3, right?
And so why two silo subgroup in S4 cross S3 is
Yeah,
isomorphic
yeah,
to
that
D4 or Z2?
it should be uh, how do we get it right? The first one.
Yes, no, sir,
The second one
previous.
is clear, right?
Yes,
1,
so
2,
I'm
3.
actually asking where we have calculated the values of K. After that, we have written two silo subgroups in S4 cross
Huh.
S3
That
is
is
isomorphic to Han.
that
Sir,
is
how did you get this?
yeah, that is apparently I need to prove, and right now I don't have a solution to this.
So
Maybe
then can you please share in the WhatsApp group
yeah,
or
yeah, maybe I can will do it later. Uh, yeah, but this thing that number of subgroups isomorphic to D4 in S4 is not that hard to show because uh, D4 to form D4 we need a cyclic group of order 2 and a cyclic group of order 4, right? Because this will be our rotation group.
so D4 is of order 8.
D4 is of order 8, yeah.
Okay, okay.
A cyclic group of order 2. Okay, maybe I will come to this question, or maybe next time I will start with this question. I need to solve this properly. Okay,
Okay, sir.
we'll do
I
it
will
right.
do okay.
Right now, my brain is not working. We'll do it later. Okay. So thank you, Akanksha. Uh, okay. Okay. Good night.
Okay, sir.